Welcome to geometry class. Today let's talk about angles in polygons. Before we get started talking about that, for a few things we've already discussed, let's just review a couple concepts. First of all, this idea of a diagonal. The diagonal of a polygon is a segment which connects two non-consecutive vertices. So if I'm looking at a polygon, let's just start with an easy one here, quadrilateral. And I want to look at a diagonal in the quadrilateral. Well, it's a segment that connects two non-consecutive vertices. So if we go A, B, C, D, we know that A and B are consecutive, B and C are consecutive, so forth and so on. But A and C are non-consecutive, and so a diagonal is a segment that connects A and C, for example. There's one other diagonal in here, and that's from B to D. So again, a diagonal is a segment, and it is a segment that connects non-consecutive vertices. Polygons are classified as convex and concave. A convex polygon has no diagonal with points outside the polygon. These are all the typical shapes we think of. For instance, maybe a pentagon that is convex might look like this. You'll notice all of the pentagons diagonals are inside. On the other hand, we have something called a concave polygon, where at least one diagonal has points outside the polygon. And we might think of something like this. You can see there's a diagonal right here, which is actually outside of that polygon. So that's the difference between convex and concave. Finally, we have something called a regular polygon. And the regular polygons are the ones we're most accustomed to. Think of a stop sign, that is a regular octagon. A square is a regular quadrilateral. We maybe talk about the Pentagon in Washington, D.C., which has this sort of very regular shape, and that is a regular pentagon. I want to be able to now talk about the sum of polygon angle measures. We've already done this in a triangle. You may recall that inside of a triangle, the measures of the interior angles always add up to 180 degrees. Of course, this would really be the measures of angles 1, 2, and 3, 180 degrees. Now we'll extend that same concept in other polygons. I've created this table here, and what we'll do is we'll fill this table in and see if we can sort of develop a pattern. Here we have some different polygons. You can see there's a triangle in the top here, in the top corner. And we already know the sum of the interior angles in a triangle is 180. So notice that there's a single triangle here. Just write the number of triangles. And the sum of all the angles in that triangle are 180 degrees. Sum of the measures of the angles. So we'll put those numbers in here. Number of sides in a triangle, 3 sides. Number of triangles, there's only one triangle in a triangle. The sum of interior angle measures we know is 180 degrees. And by the way, if this sort of seems strange, don't worry, it'll make sense as we go forward. When we look at the quadrilateral here, we can draw in a single diagonal. It doesn't matter which diagonal we draw in, but let's draw in this diagonal. You'll notice that when we draw in that diagonal, it divides the quadrilateral into 2 triangles. Okay? And we know that each of those triangles has interior angles that add up, the measure of those interior angles add up to 180 degrees. Therefore, if we added up this angle, and this angle, and this angle, and I'm not trying to suggest that they're congruent, but rather just bring your attention to them quickly, we would know that those measures add up to 180. If we did the same thing up here with angles, call these 4, 5, and 6, those add up to 180. And you can see that if we added all 6 of those together, we would actually have the sum of the interior angles in the quadrilateral. Therefore, we know that the sum is equal to 360. When we come back here, we see that if we have 4 sides, it yields 2 triangles when we draw in a diagonal, and that the sum of those angles must be 2 times 180, which is 360 degrees. When we deal with a pentagon, we can then draw in some diagonals, and we end up with 1, 2, 3 triangles. We're going back to the table in a pentagon, gives us 3 triangles, and we know that we then have 3 times 180, since there are 3 triangles and each has 180 degrees in it. We know that we're at 540 degrees total. Let's take a look at a hexagon. 1, 2, 3, 4. 1, 2, 3, 4 triangles. So going back to our chart, there are 6 sides, there are 4 triangles, and we know that will yield 720 degrees. So we now ask the question, what is the pattern that developed? What kind of a pattern has developed here? You could probably infer by the pattern that if we had 7 sides, we'd have 5 triangles, and we have 180 new degrees here, that'd be 900 total. What is the pattern? The pattern is that to find the number of triangles, I take n, and I just subtract 2 from it. So if I'm dealing with a pentagon, which has 5 sides, I subtract 2, that gives me the 3, so if I go from 5 to 3, and then I multiply that by 180 to get the total sum. 5 minus 2 times 180. We see that there's a general rule, and the general rule is that the sum of the measures of the angles of an n-gon, that is a polygon with n sides, is n minus 2 times 180. So let's just look at a couple examples. Suppose that we ask the question, what is the sum of the interior measures of the angles in an octagon? Well, we don't even need to draw a diagram for this at this point. We know that the answer will be 8 minus 2 times 180. Because 8 is the number of sides, we subtract 2 and multiply by 180. 8 minus 2 is 6. 6 times 180, 1080. So that we know is the sum of the interior measures of an octagon. Every octagon, doesn't matter what shape it is. Now let's talk about the exterior angles in a polygon. The rule, I'll state the rule and then we'll take a look at it. It says the sum of the measures of the exterior angles of a polygon, one at each vertex, is 360. We've actually looked at this rule in a prior lesson when we dealt with triangles. Let's just take a fresh look at it one more time. Suppose we had a hexagon. It doesn't have to be regular, although that may help. And we wanted to know if we were to extend these sides and add up the measures of the angles, that is angle 1, 2, 3, 4, 5, and 6. What would be the sum of those angle measures? Well, we already have a rule that tells us what the sum of the interior measure of these angles are. We know that in this case it would be n minus 2 times 180. We also know that for every side, there's a corresponding vertex. And at every vertex, if we were to add the interior and exterior angles, that would be 180 degrees, which means the sum of both the interior and exterior angles is always n times 180. So if we add exterior plus interior angles, one at each vertex, we know that that will always equal n times 180. Okay, so the exterior plus the interior, apparently we're dropping letters here. Exterior plus interior is n times 180, because there are n vertices. And we know that the interior angles is n minus 2 times 180. And so now we can actually subtract these interior measures from the total measures, and we'll arrive at just the exterior measures. Before we do that, let's distribute this n minus 2 over the 180. Let's distribute the 180 into the binomial. It ends up being 180n minus 360. That is 180 times n is 180n, and 180 times negative 2 is negative 360. Okay, so that gives us an idea of what this looks like if we do the distribution. Now we'll take the n times 180, which is actually the same as 180n. We will subtract from it the interior measures of the angles, minus 180n minus 360. And what we end up with is 180n minus 180, that's minus, that cancels. And then we have negative 360, so that's positive 60. All right. It's a rule we've already looked at, but it helps just to look at it again. What it says is that no matter how many sides a polygon has, if we take the measure of one exterior angle at each vertex and add them all together, the sum will always be 360 degrees. Let's just look at a quick example. Suppose I had a quadrilateral. And suppose we knew 3 of the exterior angle measures. So I'll just extend these so we can take a look at them. Suppose we knew that this was 70 degrees. And suppose we knew that this one over here was 100 degrees. And this one on the left up here by this upper left vertex we knew was 68 degrees. And we're trying to find x. How would we do it? Well, we know that 68 plus 100 plus 70 plus x equals 360. Therefore, we can combine like terms here. We have 100 plus 70, that's 170, plus 68 is 238, plus x equals 360. Subtract 238 from the side. We have x equal to 122. X is equal to 122 degrees. So we can use that rule to find exterior angles. The next thing we need to do is extend the polygon angle sum theorem, and the extension of that allows us to find single interior angle measures as opposed to finding the sum of them. Having the sum is interesting, but a lot of times we just need one or two. So how do we find the measure of a single interior angle? There's really two categories of problems, and they're very distinct. But let's take a look at them. The first one is, if we know all but one angle measure, we can find the missing measure by subtracting the sum of the known values from the sum of all angle measures. All right, that's a bit of a mouthful. Let's take a look at that. Suppose I had a pentagon. And suppose I wanted to know the measure of this angle here. We'll call it x. And let's also suppose that I knew the measures of these other angles. So this we'll say is 100 degrees. This one is 106 degrees. This is 105 degrees. And this one is 99 degrees. Okay. And I want to find the measure of angle x. How do I do it? First thing I do is find the sum of all the interior angles. And we know the formula for that is n minus 2 times 180. And so in this case, it must be 5 minus 2 times 180, which is equal to 3 times 180, which is equal to 540. So we know that all of these angles add up to 540 degrees. And so now we just write this out as an algebraic statement. X plus 100 plus 106 plus 105 plus 99 equals 540. And so we can combine like terms. We have 100, 206, 311, and this will be 410. X plus 410. You might want to check my math on that just to be sure. Equals 540. Subtract 410 from each side. And we find that x equals 130. X equals 130 degrees. So that's the first category. If we know all the angles but one, we can find that last angle by adding the other ones together and subtracting from the total sum of the interior angles. In the second category, if the polygon is regular, and that's important that we remember, the second category only applies when we're dealing with a regular polygon. We can find the measure of each interior angle by dividing the sum of all angle measures by the number of angles. In other words, suppose we had a regular hexagon. I'm not going to try to draw it perfectly, but you can imagine it. And we know by definition a regular hexagon has angles that are all congruent. Therefore, if we wanted to represent the measure of those angles, we would say that it's all the same number. So if we wanted to find the measure of just one of them, for instance, suppose it's x. Well, the way to do that would be to recognize that all of these are x. And so if we wanted to add them together, we'd find that x plus x plus x plus x plus x plus x is equal to n minus 2 times 180. In this case, it would be 6 minus 2, 180. Now, when we look at these x's, you can recognize that they add up to be 6x. 6x is equal to 6 minus 2, which is 4, times 180. Therefore, 6x is equal to 720. And then we can divide both sides by 6. And we end up with x equal to 120 degrees. So if we're dealing with a regular polygon, we can easily find the measure of any single angle measure by doing that. Now, this actually lends itself to a general formula that we can articulate. Notice that these x's will always be equal to, the number of those x's will always be equal to n. So there are n x's. So to find the value of a single interior angle in a regular polygon, all we need to do is take n minus 2 times 180 and divide that by n, and that will always give us a single angle measure. Okay, those are the rules that we need to know in dealing with the angles inside and, for that matter, outside of polygons. I suggest you work through a few problems, and as always, if you have any questions, let me know.